Okay, welcome back. So I would like to discuss random walks. Okay, so random walks are an important tool for studying diffusion phenomena. So diffusion has a long tradition, and so it was first observed by Brown, and he observed that a colloidal particle in a fluid performs a very erratic motion. And this is because this particle, this colloidal particle, is hit by molecules of the liquid in different directions, and this causes the movement in different directions of this colloidal particle. So this diffusion phenomenon, in order to study this diffusion phenomenon, the random walk is the simplest mathematical model. Okay, so how do we define this random walk? So imagine we have a sequence of an infinite sequence of independent and identically distributed random variables with which take value plus or minus 1, and each of these two values is equally likely. Okay, the probability 1/2. Then we build the following object, which is the sum of the first n of these random variables. And this is essentially a random walk. Okay, so so you can see this as the motion of a particle. So if you consider that n is time, and then the position of this random walk particle is Sn, and you see that at every time step, the next position is equal to the previous one plus an independent random variable, which is either +1 or -1. So at every point in time, our walk either goes up or down, and as a result of this, you will have a trajectory which this is Sn, a trajectory which takes more or less this form. Okay? So of course, for any draw of this random variable, you will have a different path. Okay, so we can think of this scheme of random walks as a scheme where the sample space is a space of or a random walk of length n of the set plus minus 1 to the n, of sequences of plus and minus 1, and each element of this sequence, each of these paths is equally likely. So its probability is 1/2 to the n. So essentially, if we want to find, if we want to solve problems that have to do with random walks, what we have to do is we have to count paths. Okay. So first of all, let us consider let us compute what is the probability that after n steps the random walk is in a certain position k. Now, if after n step the random walk is in a position k, So first of all, you notice that this is 0 if n Sn, or if say k plus n is odd. Okay, why? Because you start from 0, 0, so and then you either move up by 1 in one step or down by 1 in one step. So at every time Sn plus n either increases by 2 or decreases by 2. So it is even at n equal to 0, and it remains always even. So there is no possibility that this is that you go to a position that has the different parity of n. And if k plus n is even, then essentially you have in this random walk you should have n plus k divided by 2 steps which are positive, positive. So variables xi which are equal to plus 1, and n minus k divided by 2 steps which go down. Okay, because you see that the position at this time will be the difference between the number of steps up and the number of steps down. And so if this has to be equal to k, then the number of steps up and down should be like this. So the probability that you are in this position must be equal to the number of ways in which you can choose these many steps up out of n steps times the probability of each path, which is 2 to the minus n. Okay, so and this comes to so we come to the first important fact about random walks, and so you recognize that this is a binomial distribution. And we know that for the binomial distribution, the expected value of Sn is equal to n times the expected value of x. And this is equal to 0 because the expected value of x of this xi is equal to 0. Whereas the variance of Sn is n times the variance of the xi, and the variance of the xi is equal to the expected value of xi squared. Xi squared is equal to 1 because xi are plus or minus 1, minus the expected value of x squared, which is 0. So this is just equal to n. Okay, so the first thing that you learn, and this is the key fact, is that the expected excursion of a random walk after n steps is of order square root n. Okay, so if this is so after n steps, you expect that this should be of order square root n, because this is the standard deviation. Okay, square root n is the standard deviation. Okay, so this is something that you should really keep in mind. Also, the other thing that we know is that the binomial distribution, when n gets larger, converges to the Gaussian distribution, so that we can even be more precise. So if we imagine that we repeat this, we consider the limit when n goes to infinity, and let me write n as a continuous time variable t divided by dt. Okay. So this tells you that if you take 1 over square root n, which is times Sn, computed in n, which is equal to t divided by dt, and then take the limit when dt goes to 0, what happens? Well, what happens is that n, if t is fixed, then n goes to infinity, and this variable Sn, which is a binomial random variable, because of the Moivre Laplace distribution, converges to a Gaussian random variable, and so in this way you can define a random variable that depends on a continuous time t, and this is called the Wiener process. So here we are going to discuss random walk in discrete time, but you can also discuss the same property in continuous time. We will get back to the Wiener process and random walks in continuous time in the course, in the next lecture of this course. But the key point that I want to stress is that, say, if you take, for example, if you take a fixed t and 2 dt which are different but small, and you plot this combination here, you do a numerical simulation, and you plot this combination here, you should not be able to see which of the two curves that you obtain correspond to the smaller or to the largest dt, provided that both these time intervals are very small. Okay? And this is this tells you essentially that the properties of random walks for large values of n are going to become universal. But we will come back to this. Okay, so let's make a few examples of random walks, or how we can use random walks. So the first one we have already seen. We have discussed this problem of the theater in Moscow. Okay, so let me discuss other problems. So one is the Pallot Theorem. So imagine that you have an election. You have two candidates. So candidate P gets P votes, and candidate Q gets Q votes. And Q is less than P. Okay? Now imagine that now this is, you look at the counting process, and you look at the difference, so you ask the following question. You look at the counting process as votes are counted, and you ask the following question. What is the probability that P always leads Q in the counting? Okay? And so the idea is that we can recast this event in terms of a random walk. So if we call Sn the difference of the number of votes for P minus the number of votes for Q, as counting of the votes is done, then we essentially will have a random walk, because at every new vote which is counted, it will be either for P and then this curve will go up, or for Q and then it will go down. Okay, so we have a random walk where the n is equal to P plus Q, and this point is at so this distance here is P minus Q. Okay. And the Pallot Theorem tells you that this probability has a remarkably simple form, which is P minus Q divided by P plus Q. Okay? So the second thing that interesting example of random walks is what is called the Kolmogorov Smirnoff test. So what is the probability? So what is the problem? Okay, so the problem is the following. So imagine that you have two samples. Say A1, AN, and B1, Bn. So these are samples of n numbers, and they are, for example, measurement of a certain quantity in two different conditions, for example. So, for example, you can think of you have n patients which have undergone some treatment, and then you measure something like blood pressure on these n patients. And then you have n patients who did a treatment and which might affect the blood pressure. And so the question that you ask is what is the probability? Can we say whether these numbers here come from the same distribution as these numbers here? Okay, so these two, can we say whether these two samples are independent draws from the same distribution or not? Okay, so the idea of the Kolmogorov-Smirnoff test is to build the following functions. Say A of x. Let's say that A of x is the number of I such that AI is less than x. So we take this set, the number of the set of I such that AI is less than a certain value of x, and we count how many of these numbers here are less than x. Then we can do the same for B. B of x is the number of I such that BI is less than x. Okay? Now, the first thing that we observe is that, so if this AI come from a certain distribution, then the expected value, of course this A will be, if these are random variables, then this A will also be a random variable. You can take the expected value of this random variable, given that the AI are drawn from a certain distribution. And you can easily convince yourself that the expected value of A of x is equal to n times the probability that AI is less than x. Okay, indeed, this A of x is n times the empirical distribution that you can estimate from the sample. And this tells you that the expected value of the empirical distribution is equal to the true distribution. Okay? Now, the idea of the Kolmogorov-Smirnoff test is you will have two curves here. One which is the curve of A of x. So if this is x, this would be A of x. And the other one, so how will this curve be done? So this curve, so imagine that here you have the different values of A. Here you plot x. And so the curve A of x will be 0 up to this point, and it will go up by 1, then it will go up by 1, etc., etc. So this is the curve of A of x. Okay. Okay, so this will be A of x. What is the curve B of x? Well, imagine that the points B of x will be, for example, these ones. So they should be of the same number: 1, 2, 3, 4, 9, 6, 7, 8, and let's put another one, 9. Okay. Then the curve B of x will be 0 up to here. Then it will be 1, then 2 up to this point, then 3, then 4, 5, 6. Okay. So this is the curve. So this is the curve B of x. Okay. Maybe I can plot it with a little bit of. Oh, sorry. Okay. So this one. I should have colors, but I don't have. Okay, so what is the idea of the Kolmogorov-Smirnoff test? Is, well, let's look at the soup on x of A of x minus B of x. So how big is the difference between these two functions? Okay, so we look at the value of x. such that the difference in absolute value between A of x and B of x is the largest. And what is the idea? So imagine that these two really come from the same distribution. Then can we say, can we compute the probability that this difference is less than a certain number xi, conditional on this hypothesis? The hypothesis H is the hypothesis that A's and B's come from the same distribution P of x. So can we compute this probability here? And well, the idea is that in order to compute this probability under this hypothesis, then you can map this problem into a random walk. So in the following way, so you start from this point, and then every step is one of these points, whether you either have an A or a B. Okay, so you proceed in steps. So if you have a B, then you go down. If you have an A, then you go up. Then you see that this then is a random walk, and generically, so you will have, but this random walk should have the property that because the number of points in A is equal to the number of points in B, then the number of steps up is equal to the number of steps down. So after 2n steps, you should be again back to 0. Okay, so you can compute a random walk also for this case, and then this problem here becomes the problem of understanding what is the probability that if you fix xi, what is the probability that this random walk always stays between plus xi and minus xi. Okay. Now this, you see, the important point of this is that this problem, this probability, can be computed just from the property of a random walk, and without any reference to whatever is the probability distribution of x, of the A's and the B's. Okay, so and of course, say if we can compute. So we can compute this probability from the theory of random walks, and we can find out what is the largest excursion that we expect from this random walk. Okay. And if the excursion that we measure in the data is the real number that we get in the data, because this can be computed from the data, is much larger than what we expect, then we will reject this hypothesis. But if we get a number which is consistent with what we, that is a value which has a rather large probability, then we cannot reject the hypothesis that these two samples come from the same distribution. Okay, these random walks that come back to the origin, they are not called walks, they are called bridges. So in this case we talk about random bridges. Okay, so what is the idea? So what I will do now is to discuss some ideas which are based on just counting, on how do you solve these problems. Okay, later on we are going to discuss how do you address these problems using generating functions. Okay, so the main result that we are going to use is called the reflection principle. So the problem is stated so in the following way. So imagine that we take 2 points, A and B, which are both on the positive axis, positive semiplane above the x-axis. And then we want to count the number of paths that from A to B, that go from A to B, the number of random walks that go from A to B, crossing the origin, crossing the axis, so that they either touch or cross the x-axis. Now, so let's call this, in this way, the number of paths that go from A to B crossing the t-axis, okay? So then the reflection principle tells that this number here is exactly equal to the number of random walk of paths that go from a different point A prime to B, where this point A prime is what you get is this point A reflected around the origin. Okay, so it's the point where, so if this point A has coordinates A and alpha, then these points A prime has coordinates A and minus alpha. Okay, where both A and alpha are integers. Okay, so this is a quite remarkable result because you see, computing all the paths that go from A to B, crossing the origin, crossing the axis, is a complicated problem because you don't know where they cross the origin. So it's a condition that can occur in all these intervals between A and, if we call this B, between A and B, okay? Whereas computing this is rather easy. Actually, we already know that this will be the number of steps, which is A plus B, divided by the difference between the K, which is essentially this difference here is alpha minus, is beta minus alpha. So this is A plus B plus beta minus alpha choose 2, okay? So, so what is the proof of this statement? So the proof is rather easy. it is based exactly on the reflection. That is, for any path that goes from A to B crossing this axis, there will be a point T where this path first crosses the axis. Okay, so you can take this part of the paths from A to T and reflect it with respect to the axis and get the reflected path, okay, which would look like something like this. Okay. Now you see there is a one-to-one correspondence between paths in A and T and paths from A prime to T. So if you want to count the number of, and the rest of the path is exactly the same. So this tells you that because this corresponds is one-to-one, the number of paths that goes from A to B crossing the origin is equal to the number of paths that go from A prime to B, because you can make this association one-to-one. Okay. Now let us see how we can use this to solve the Pallot Theorem. Okay, so in the Pallot Theorem we are interested in paths that go from in P plus Q steps goes to the point where beta is P minus Q. Okay, so essentially we can use this the reflection principle by observing the following thing. So that each path, if we want to count these paths, so each path that satisfies the condition of the Pallot theorem has to pass through the point A, which is 1, 1. Okay? Then, essentially, if we want to compute the number of paths that go from A to this point B that do not cross the x-axis, then what we have to compute is all the paths that go from A to B and subtract from this the number of paths that go from A to B but that cross the x-axis. Okay? But this is equal to the number of paths that go from the points A prime to B, where A prime now is the point with coordinate 1 and minus 1. Okay? So, what are these? So the number of the number of paths that go from A to B is P plus Q minus 1, and then out of this P plus Q minus 1 there are P minus 1 steps up. And this one, instead, if you do the calculation properly, is P plus Q minus 1. But then now I've removed one step down. Okay, so this is choose P. Now this you can express it as P plus Q minus 1 factorial, P minus 1 factorial, Q factorial minus p minus plus q minus 1 factorial p factorial times q minus 1 factor. So now you see that if you multiply and divide by p plus q both terms, and if you multiply and divide these by p and these by q, so so what you get is here you get p divided by p plus q times p plus q choose p, and on the other side from this you get minus q divided by p plus q times p plus q choose p. So this is exactly equal to p minus q divided by p plus q times the number of paths that go from the origin to B. So if you want to compute this probability is just equal to the number of paths that go from A to B without crossing, divided by the number of paths that go from the origin to B. And it's exactly P minus Q as B plus Q. Okay? So there are other use of the reflection principle that solve other problems. So for example, a Kolmogorov-Smirnoff test, you can compute this probability by a repeated use of the reflection principle. And what you get is that the probability that 1 over square root n times the sup over x, so the maximum of the difference probably that this is less than t, asymptotically for n going to infinity, for n large, as an explicit formula which is 1 minus 2 times the sum k from 1 to infinity of minus 1 to the k minus 1 e to the minus 2k squared times t. Now this is a complicated formula, but you can compute this number at any desired precision because this is a rapidly convergent series for any value of t. And then you can compute this probability. So you can know whether this hypothesis is true or not for these two samples, irrespective of what is the distribution of A and B, because this is a universal result.